Assalamu alaikum student. Today's lecture is differential pulse code modulation, which is also known as DPCM. It will be covering CL1 and it is present in 6.3 of your textbook. In this lecture we will discuss DPCM in detail and we will discuss why there is a need to propose DPCM, then what was the reason that's why DPCM was proposed as a solution, then we will have a look at its encoder and decoder and how it can improve the SNR, and at the end we will study its different advantages. So let's start with DPCM. Actually, it may be observed that the samples of a signal are highly correlated with one another. This is due to the fact that any signal does not change fast. This means that its value from present sample to next sample does not differ by large amount. The adjacent samples of the signal carry the same information with a little difference. When these samples are encoded by a standard PCM system, the resulting encoded signal contains some redundant information. We will discuss it later, that how this redundant information is not required. But for now you can have these two examples. We have signal A and signal B. Here our samples are far from each other, whereas in signal B the samples are relatively close. So we can say that in signal B the samples are much correlated with each other, because the difference between two samples is very small, which is not the case in signal A. So if we are taking less samples, bandwidth requirement is also less, as you can see for signal A, less number of samples mean less number of bandwidth is required. But the drawback is that at the receiver side signal reconstruction is also very difficult. Therefore signal B is the required scenario, because here samples are more correlated, and then because of this signal reconstruction is very easy at the receiver side. Now in PCM we know that each sample is encoded and transmitted. We have to transmit all samples, and for those purpose all samples are encoded and then transferred. So from this example we can observe that what is the PCM disadvantage. Actually here you can see that different samples are carrying the same information, so it means redundancy is being incorporated. As you can observe that sample at TS, 5TS and 6TS, they all samples are carrying information which is 0, 1, 0, and same information is carried by 3 samples, whereas 2TS and 4TS, both of these samples are also carrying the same information which is 100. It means if we are basically introducing redundancy and we are transmitting redundant information in a scenario of pulse code modulation. If this redundancy is reduced, then overall bit rate will decrease and the number of bits required to transmit one sample will also be reduced. So this is a huge benefit. And what is the solution for this and how we can achieve this? Therefore, a new scheme, digital pulse code modulation, was proposed, and the main principle of DPCM is that in DPCM we reduce the redundant information, and to achieve more compression only the difference between the successive samples is transmitted. So now we are not transmitting each sample, but we are transmitting the difference between two samples. So this is the main principle, working principle of DPCM. The difference between working of PCM and DPCM can be understood from this example. Suppose we have a signal which has samples like 3.1 volt, 3.5 volt, 3.4, 2.9, 2.5, 2.1 and 2.2. So these are different samples of any sinusoidal signal. Now in case of PCM, we have to quantize these samples, and then different binary codes are assigned to each sample, and all of these samples will be transmitted. It means the binary code which is assigned to each sample will be transmitted. But DPCM does not work in this manner. Here in DPCM, instead of transmitting each sample, only the difference between two successive samples will be transmitted. Like the difference between 3.1 and 3.5 is 0.4 volt. So instead of transmitting 3.1 volt and 3.5 volt, we will transmit 0.4 volt. Then the next difference is 0.1 volt, so 0.1 volt will be transmitted. After that 0.5 volt, 0.4 volt, 0.4 volt. So in this way the difference between different samples will be transmitted. Now the question is how this approach helps us in saving our bandwidth, and how it helps us in any transceiver scenario. Suppose you have 4 volt, two samples, one is at 4 volt and then the other is at 4.1 volt. Now if we have to transmit 4 volt and 4.1 volt, we know that it is a high voltage, so it means more number of quantization levels are required. So more number of quantization level means L is increasing. So when L is increasing, then according to the formula, L is equal to 2 raised to power n will also be increasing. So it means more number of bits are required to that will be assigned to each sample. This was the case with PCM. But on the other side we have DPCM, where instead of transmitting 4 volt and 4.1 volt, we will transmit 0.1 volt, which is the difference between two samples. We know that the difference between adjacent sample will always be a less value. So it means low voltage, because 0.1 is definitely low, very low as compared to 4 volt or 4.1 volt. So low voltage means less number of quantization levels are required, and when less number of quantization levels means L is less, so it means N will also be less and less number of bits per sample will be required. So in this way we are basically assigning less number of bits for DPCM as compared to the PCM, where a large number of bits are required to each sample. So in this way the difference between two samples is more beneficial as compared to the scenario where all samples are transmitting and where we have high voltage and large bits are required. So let's have a look at DPCM encoder or transmitter. This figure is the DPCM transmitter. DPCM, that is differential pulse code modulation, works on the principle of prediction. The value of present sample is predicted from the past samples, and the prediction may not be exact, but it is very close to the actual sample. This figure is showing the DPCM transmitter. Here we have here in start we have analog signal, which is x of t, and when this x of t passes through sampler and it is converted into x of nts. Now the comparator basically finds out the difference between the actual sample value, which is x of nts, and the predicted sample value, which is x bar of nts. So this is the predicted value which is coming from prediction filter. So this comparator basically compare both of these values, and then it gives us the result, which is termed as error, and it is represented as e of nts. Now this signal will pass through quantizer. It will be quantized and it can be represented as quantized error, and it is denoted as EQ of NTS. So here we have prediction filter, so which is basically predicting the value. Now EQ of NTS will be added to this predicted value, and then XQ bar of NTS will be added as an input to the prediction value. After this, the output will be given to encoder, and it will result in DPCM output. So here X of NTS is basically sampled signal, X bar of NTS is predicted signal which is coming from prediction filter, then E of NTS is the error signal, which is basically the difference between sampled signal and predicted signal, and then EQ of NTS is the quantized form of error signal. E of NTS is the error signal which is known as prediction error. It can be defined as E of NTS is equal to X of NTS, which is the sample signal, and then X bar of NTS, which is the predicted sample signal. Now the quantization error signal, which is EQ of NTS and previous prediction X bar of NTS, are added and given as input to the prediction filter, also denoted as XQ of NTS. Now quantized error signal is very small and it can be encoded by using small number of bits. Thus the number of bits per sample are reduced in DPCM, which is the main advantage of DPCM as compared to pulse code modulation. The quantizer output can be written as EQ of NTS is equal to E of NTS plus Q of NTS. We can say that Q of NTS is the quantization error. When this quantization error will be added to E of NTS, then we get a quantized error signal, and it is obvious that after passing through quantizer, some error will be introduced to the error signal, and it will result into quantized error signal. Now the prediction filter input can be given as XQ of NTS is equal to X bar of NTS plus EQ of NTS. So this quantized error signal along with the previous predicted value will be added to get the current quantized XQ of NTS, which is the input to the prediction filter. If we substitute the value of quantized error signal from equation 2 and substitute this value in equation 3, then we get a new equation which is XQ of NTS is equal to X bar of NTS plus E of NTS plus X of NTS. Now put value of E of NTS from equation 1 in this equation, and we can see that X bar of NTS will be cancelled out with minus X bar of NTS, and we will be remaining with XQ of NTS is equal to X of NTS plus Q of NTS. So we left with the equation XQ of NTS is equal to X of NTS plus Q of NTS. This equation is showing that quantized version of signal XQ of NTS is basically the sum of original sample value X of NTS and quantization error Q of NTS. So this is the result which we are getting from this. Now move on to DPCM decoder or receiver. This is the block diagram for DPCM receiver. From this figure we can observe that the decoder first reconstructs the quantized error signal from incoming binary signal. Because we know that the DPCM signal is basically a binary signal, and the decoder, the first task of decoder is to reconstruct the quantized error signal from the incoming binary signal. The prediction filter output and the quantized error signal are summed up to give the quantized version of the original signal. Thus the signal at the receiver differs from actual signal by quantization error Q of NTS, which is introduced permanently in the reconstructed signal. So the signal XQ of NTS will pass through low pass filter and it will be converted into original analog signal. So this is how the receiver for DPCM works. The output signal to quantization noise ratio for a DPCM system may be defined in a similar manner as that for a PCM system. The signal to noise ratio can be calculated with the formula SNR is equal to mean square value of signal over mean square value of quantization noise. But here, since we are talking about noise, so the mean square value is basically equal to the variance. Therefore SNR will be defined as sigma x square over sigma q square, where sigma x square is the variance of original input, that is x of NTS, and sigma q square is the variance of quantization error q of NTS. So we can, if we want, so we can rearrange this expression, and it can be written as SNR is equal to sigma x square over sigma e square and sigma e square over sigma q square. Now we can say that sigma x square over sigma e square is GP, which is prediction gain produced by differential quantization, and SNR of P is the prediction error to quantization noise ratio. So output SNR is equal to GP into SNR of P. So GP is basically prediction gain, and it is defined as sigma x square over sigma e square. Now we want prediction gain to be as high as possible. However, sigma x square, the signal power, is the variance of the signal is fixed, so the only other possibility available is to reduce sigma e square so that the overall value of the GP should be high. Therefore, care must be given to design a prediction filter. Now we can discuss the advantages of DPCM. Difference is encoded and transmitted, so a small different voltage is to be quantized and encoded. It requires less number of quantization levels, and hence less number of bits are required. Thus, signal bandwidth of DPCM is also less than that of PCM. Thank you.